Okay, so we're going to explore an infinite geometric power series. We talked about infinite geometric series. We're just saying that we're going to look at a power series. That means that the expression we see to the nth power has a variable in it, such as x. And we have seen this a couple times before. And previously, we'd look at a term that's in terms of x, but now we're looking at a series that is in terms of x. So this particular series is said to be centered at x equals 0. The reason is because there's a function that is being represented here. We'll go over how to get that function. But in any case, there's a function, and that function is bounded within the unit circle. And the reason for that is because in order for us to actually find the sum of an infinite series, a geometric series is what we went over to find that sum. What happens is that we can only do it for an interval of convergence, okay? This is ensuring, this is the same thing as this, that it is indeed a value, this is r by the way, that is less than 1. So in terms of x, this would be along the unit circle, and I know you're not used to seeing it this way, but an absolute value is a way in which we can look at numbers in which there are no positives or negatives. Everything looks at as a positive number. The same thing when we're working with squares. So this is saying that it's bounded within the unit circle. Okay, so this is going a little bit further beyond explaining why we use the word centered. This goes into BC calculus. But for right now, all you just have to understand is that this is representing an infinite geometric series. It's a power series because it's a variable x. And this one we're looking at is centered at x equals 0. Okay? So now just to point out, the next one that I'm showing you here, this one is not centered at x equals 0. See, the expression is now x minus a, so if you set that equal to 0 and you solve, you find that the center is x equals a. So there's a way in which we can find the center. What is important is rewriting the summation and start to go through what was that function I was talking about and all these other things that are important when we go through an infinite geometric power series. Okay, so this is what we want to do today. We want to be able to find the function f of x represented by our geometric power series and find its interval of convergence. We want to know how the geometric series becomes a series of constants, okay, just numbers. So that means that we're going to use the sum because the sum gives us a number, okay, so that gives us a value. So we're going to use this example here. Notice the wording of the problem. So I will always word the problems exactly this way to not confuse you what we need to do. We're going to find f of x, find its interval of convergence, simplify, and show it's a series of constants. Okay, so let me write out this problem. This is our example. Let me squeeze in the word example. It's in there. Here we go. Okay. So write down step 1. Step 1 is to rewrite the power series. You don't always have to do this particular part of step 1, but you always need to do a step 1. The first thing I'm going to do in step 1 is notice that my exponents are the same, so I'm going to combine the bases and say it's 1/4 times x minus 2 to the nth power. So now I have one expression to the nth power. That's very important. The next part, that means like if this is already done for you, you must write what it equals. So this means that it equals, we plug in 0. We plug in 0 into the expression and we get 1. That's where the 1 was coming from. Okay, and you can write it like this, or you can just write it's 1 plus. So we're rewriting the sum. Okay, we're rewriting the series here. It's 1/4 x minus 2 to the first. Okay, and I would do one more just to show that it is to the second power. Okay, and what I'm going to do here is that I already simplified these expressions, so I'm just going to cross them out. I don't need them here anymore. So what this equals, this series, equals 1 plus our next term and our following term, and it continues. So don't forget the ellipses at the end. So that's step 1. Step 2, we want to find r. So in order to find r, we're going to take the expression that we have that's raised to the nth power. That is r. And since we rewrite it, it's already kind of expressed for us. So you're just re-emphasizing it. Step 3, using the sum formula for an infinite geometric series, find f of x for this interval. We're going to go back to that interval. Okay, so we want to find the sum. So our sum for an infinite geometric series is our first term, which in this case is 1. It's not always, be careful. It's 1/1 minus r, which is what we expressed in step 2. Okay, what I need you guys to do is simplify this. Okay, so our denominator needs to look a lot more polished than what it is. This is 1 minus 1/4 x plus 1/2, okay, or 2/4 if you want to make a common denominator. And so we keep simplifying. You must absolutely simplify this, okay? So eventually we're going to do keep, change, flip. So 1 is the same as 4/4, so it's going to be 6/4 minus 1/4x. So it does have a common denominator of 4. So the keep, change, flip here means that we're going to have 4 in our numerator and 6 minus x in our denominator. Okay, this is actually our function, f of x. Okay, so we found that. This is step 3. And I need to erase some things to get to step 4. So step 4, we want to find that interval of convergence. So that's what I was pointing at over here. So we're going to take r and put it between -1 and 1. Again, r was found in step 2. Be careful of that. And we're going to simplify this as well. So I multiply 4 on both sides. And I add 2 on both sides. So this is my interval of convergence. Okay, so that function is going to be used for values that are between -2 and 6. Okay, 5 is actually like our answer for this problem. I'm going to erase some more. Okay, so since there was a lot to write for number 4, I just decided I'm going to erase the whole thing. So it's going to start off the same way. Given the infinite, you can write geometric power series because that's what we're working with. The given one that is, well, given to you. It converges to, and this is going to be our function, so it's f of x is equal to, what was it, 4/6 minus x. Okay, 4 negative 2 is less than x, which is less than 4. Okay, I believe that's what we got in the last step. So we're kind of pulling everything together. And this is actually step 5. Let me erase that and fix that. I apologize. I remember I left off at step 4, so that would make this step 5. So step 6. This is kind of a check. I tell students this is kind of a check. We're going to choose an x value within the interval of convergence. So let's say x equals 0. This is a good value for x because it's not the center. I'm going to go back to what that means. So number 6. And actually number 7 kind of ties together. So we're going to say x is equal to 0. So it's not the center. The center would be a value that would make this expression, and I'll pull this in from before, okay, equal to 0. Well, particularly this part, because we need to solve for x. And so x equals 2 is not a good value, okay? Many times what that does is that would make your first value an indeterminate, and you can't add anything to something that is undefined or an indeterminate, and so there is technically no sum. Even if it is a value that exists, it would be 0, and then adding 0 with 0 with 0 with 0 with 0 is saying that your sum is going to be 0, and that's not always the case. So you never really want to pick that center. So we reject anything that becomes the center, and we pick a different value. This value is not only in the interval we have here. Let me erase this and highlight this. It's also a good value because it's not the center. So remember both things, okay? Remember it's a value that has to be in this interval, and it cannot be the center. So I also chose 0. It's one of the easiest values to work with, okay? So try to pick a value that's easy to work with. Sometimes you do have to pick decimals or fractions such that it is in the interval, but usually just pick something you can work with, like a half. Anyway, so if x is equal to 0, then we're going to plug that into our sum formula and our function. So if we plug it into, I'm trying to see which one I'm saying here. If we plug this into our sum value, okay, our sum was 1 over 1 minus 1/4, quantity x minus 2. So let me erase that x and put in 0. Okay, then that's going to give us, let me make that a minus sign, that's going to give us 3/2 in the denominator, so that's 2/3. Okay, and when you plug it into your function, change color here, 4/6 becomes 2/3. That should be the same, okay? Your function value should equal your sum. So I tell my students that's the way we kind of check it, but it is part of the problem that was being asked for you to be done, so you must do this part, okay? It shows that you have a series that becomes constants, all right? So good luck, be careful, and have fun.